So we have a RAN intelligent controller overview. We learned also in the previous course that the working groups for ORAN are as follows. Mostly for these courses, the important ones are working groups 1, 2, 3, and 1, 2, 3 until 5. Okay, so yung working group 2, that's non-real-time RIC and A1 interface. Remember, A1 interface is the one connecting the non-real-time RIC and the near real-time RIC. And the purpose of this is for radio resource management, higher layer procedure optimization, policy optimization, and AI models. But for near real-time RIC and E2 interfaces, they are prepared by the working group 3. It is for control and optimization of the RAN elements and any fine-grained data collection over the E2 interfaces. Okay, so now let's proceed on the discussion of the RIC. Over time, there were already controllers in previous generations. So like in 2G, there is what we call a base station controller. And then in 3G, there is a radio network controller. And then in 4G, there's really no separate controller element. And there is an interface called X2 to connect to different E node Bs. And then for 5G, we have a G node B. Okay, so are just like the base stations. And then due to the combination of the network virtualization, eventually we were able to introduce the RIC. 5G applications often require low latency. So 5G specifications require the use of network function virtualization and software-defined networking, and for the purpose of optimization for control of the RAN. So this RIC enables a lot of functionalities like the network intelligence, resource control, resource assurance. And this is originally defined for 5G. The RIC is originally defined for 5G, but it can be modified or it can be updated to support not only 5G. The important thing is it can support the interoperability of different hardware and software components. It also leverages data analytics and AI platform for better resource management, such as for optimization like QoS, quality of service, slicing, network slicing, and mobility. So essentially, it is for optimization, and ultimately, this is to have an efficient RAN architecture or a radio access network. Okay, so there are two different frameworks two different RIC frameworks. One is the non-real-time RIC, the other one is the near real-time RIC. The non-real-time RIC is located on the SMO framework, and it communicates to other components via the A1 interface and O1 and O2 interface. Just go back to the Open RAN architecture, the ORAN architecture to verify the interface. This is used for tasks that require greater than 1 second of latency, like as mentioned earlier, more on configuration management, data analytics, maybe for forecasting. And this non-real-time RIC hosts what we call R apps. The R apps are possible proprietary applications to perform certain functions that would use the data collected by the near real-time RIC. Okay, so this can also include policy guidance, configuration management, and others. Okay, but what you need to know is anything greater than 1 second of latency that should be handled by the non-real-time RIC. Next, near real-time RIC framework is connected to other devices, other components. It's connected to the non-real-time RIC using the A1 interface, and then connects to others using the E2 interface. Now, if we go back to the architecture, there's an E2 interface here connecting the near real-time RIC to the CU, the DU of different nodes. Okay, so the near real-time RIC supports tasks that are less than 1 second of latency, like for example, radio resource management and other functionalities for the eNode B and the gNode B. Remember, this is like the base station for 4G and 5G. So we have here also X apps. This is the equivalent of our apps, but in near real-time RIC. So non-real-time RIC, R apps, near real-time RIC, X apps. Okay, so this is the general ORA non-real-time RIC architecture. So you can see non-real-time RIC is on the SMO side. It's connected to the near real-time RIC using A1 interface. And then later we'll discuss further on this. And then we have here the near real-time RIC. This one contains the X apps. Its southbound interface is E2. Northbound interface is A1 towards the non-real-time RIC. All of these are defined in the working group 3. Okay, so now let's proceed to the functional split. Remember what I said before? We know that the remote radio unit is separated from the baseband unit and are connected using the front hall interface. An example of this is the CPRI. But eventually, they realized there is a need to further split the functions of the BBU into CU and DU, so distributed unit and centralized unit. The separation is summarized by the technical report from 3GPP, the TR 38.801. Okay, so the split RAN architecture wherein BBU is split into DU and CU, and then there is now a new interface called the mid-hall interface. So now we have the front hall interface, the mid-hall interface, and the back-hall interface. Whatever the functions of the CU, DU, and RU or RGU, they are defined depending on the needs of the mobile network operator. Okay, so we will discuss this in the next few slides. Okay, so what is functional split in 5G? Different protocols or different protocols reside in different components. Among the three, the RU, the DU, and CU. So split implementations make it more flexible and easier for mobile network operators to fit to specific deployment constraints. Now, maybe they just prefer to have the RU and DU at the same location, but the CU at a different location. Or maybe they can have the DU and CU at the same location, but the RU is separated. So depending on the needs of the mobile network operators, they can select which design that they want. Okay, so these are key factors in determining the split choice that the MNC would want: the specific quality of service, the user density, and the transport network. Okay, so these are the key factors for that. Okay, so here are the overview of the functional split. So for the monolithic RAN, we just have the BBU as is, same big block, and then we have the radio unit. But because of the technical report 38.801, the BBU became a CU and DU. The RAN functional split divides the monolithic RAN into three parts instead. You have the radio unit, distributed unit, and the centralized units. So we have a separation here by the mid-hall, and then we have the front hall here. So if the mobile network operator decides to have a split here at the bottom, between the RU and the CU DU, then that is what they call a low layer split. It's at the bottom. It's a low layer split, LLS. If the mobile network operator just decides to split at the top, combining DU and RU in one main part, we'll just have a high layer split. So high layer split at this part. Okay. Combining the two, if you need to do separation for all three components, then you can use dual split. A combination of HLS and LLS. Okay, so let's first look at the high layer split options. So there are two options here, options 1 and options 2. For option 1, that is when we separate the following protocol. Okay, so the RRC and SDAP are on the centralized unit. So the functions here, the network functions, virtualized network functions, are on the CU COD server or CODS hardware, while all the others will be performed on the RU-DU system or RU-DU hardware. Okay. So here there are only two blocks, the CU and the integrated DU and RU. F1 is the interface between CU and DU. Okay, so this is the mid-haul interface. This is an open interface. This kind of deployment scenario, or rather these two deployment scenarios, options 1 and 2, are best for high capacity or capacity use cases in dense urban areas. And this one usually has a large dependence on the front haul performance than LLS. Okay. So the option 2 is just you consider PDCP protocol also in the C. Okay, so next, if you consider low layer splits, what you do is you split the lower part of the RAN protocol stack, and then you'll get two blocks. One is the integrated CU and DU. The other one is the RU. Okay, so this is option 8. Only RF is assigned as the function of the remote radio unit. And then the PHY, MAC, RLC, and so on are assigned to the CU and DU. So in this kind of setup, LLS utilize less than perfect front haul interface. Then this one is CU, DU, then RU. The lo-fi is performed at the RU, and then the hi-fi is considered at the option 6. So for option 6, there's a specific front haul interface. Usually it's the NFAPI. It's a functional application platform interface that is provided by SCF or Small Cell Forum. It is to allow SCU and SDU to connect to any SRU. Option 7 often use eCPRI frontal interface. And then option 8, later we'll see the option 8. There's a special option, sub-options for option 7. We have here the split option 7.3, split option 7.2, split option 7.2x, and 7.1. So they can further specify even on the particular protocol the certain processes. So maybe they want only this split here, or so on. Okay. So this is a more specific split for option 7. Then option 8 uses a CPRI interface. This was originally vendor specific, but can also use eCPRI for open interface. Okay, so to summarize, these are the different functional splits and where we split the RAN protocol stack. Option 1, 2, 3, 4, 5, 6, 7, 8. It's less common to use option 3, 4, and 5. So it's more common to use actually this high layer split and low layer splits. We can also see the interface since for options 1 and 2, we have the separation of the CU and the DU-RU. Therefore, we have a mid-haul interface. This is the F1. F1 is defined by 3GPP. And then for the low layer splits, the front haul interface connects the RU and the CU-DU. And depending on the option, we have different interfaces that is best used. For SCF, Small Cell Forum, we have NFAPI. For option 7, we have eCPRI. And option 8, eCPRI. So with all this flexibility, it makes it easier for operators and vendors to select a split variant according to their design and operational needs. Maybe they only need more RF devices, then they can just focus on option 8. Or maybe they only have existing infrastructure for option 6. Then they need a connection towards the RU with the functions low-fi and RF. This is another way to view the functional split options. This is option 1, 2, 3, 4, 5, 6, 7, 8. It is like it's just rotated. You still have your CU, then DU, and RU. Okay, this pertain to the OSI layer, OSI layer 1, OSI layer 2, and OSI layer 3. Okay, so here are some sample deployment scenarios. If you have all of them separated, then that means there's an independent RU, DU, and CU locations. So the front hole, the mid hole exists. Usually the mid hole is kilometers, this also in kilometers. For another deployment scenario, we're in co-located or CU and DU are co-located. That means that there's actually no mid hole here. Then we only have front hole. What if we have co-located DU and RU? Then we don't have any front hole really, and we have mid hole here. Usually the front hole exists, but just tens of meters within the same building maybe, or this mid hole is connected like fiber optic cables. It's also possible to have all of them in one big block like this, RU, DU, and CU integration. Oftentimes, this is for small cell or hot spot scenarios. Hot spot scenarios. So small cell forums also define the functional split. They look at it as either an integrated solution or a disaggregated solution. When they say integrated solution, everything, all the three components, the RU, CU, DU are in one big product. But there are disaggregated solutions like this 2-product solution and 3-product solution. 2-product solutions are usually based on the options 2, 6, 7, and 8, where in each option there are only 2 blocks. Then in the 3-product solutions, it's usually the combination of the low layer split and the high layer split. Now, that's why there's a combination here. Option 2 and 6, option 2 and 7, and option 2 and 8. Okay, so other than the setup, now there are other reasons to choose different functional splits or different splits. No? It is depending on the delay, the performance, the bandwidth. But we'll not be able to go into detail on this.